This conference will now be recorded.
Okay, so good morning everyone, and welcome back to a fresh new session on credit risk modeling. And over here, so since the last session, what we had started was we were discussing the set of possible interview questions, right? So the interview sessions are broadly divided into 5 to 6 broad sections of questions, right? And you can think about them as you can rather club them up as 2 to 3 rounds of interviews, right? So, in a given round of interviews, you can expect questions across these 6 groups of these 6 groups, depending on whatever you are doing, whatever you are learning. So over here, what we have is we have so the 6 broad areas on which questions generally tend to come are the overall walkthrough of the CV and the soft skills, basic statistics and econometric skills, model development and validation skills, supervised and unsupervised machine learning models, tool skills like SAS, SQL, Python, Excel, and regulatory frameworks. Right. Now over here, what we are going to do is we what we have started doing is we have started listing out the key type of questions that can actually come across, right? And in the topic that we discussed last class, it was broadly divided into. So we had broadly discussed 2 topics in the last class, right? So one of the topics that we had discussed was the central tendency and dispersion, and the second topic that we had discussed over here was probability theory and distribution, right? And within probability theory and distribution, we had discussed some basic questions. Also, as a part of the discussion last session, what we had done was I had shared out the location for the the Word documents, the documents on statistical content, the readings on statistics, right? So, for your reference, I had shared that out, right? So, if I come to this particular drive. So please note that 1.1, 1.1 is going to be your final drive, because whatever videos we have done this year, like whatever the new videos are, I am uploading them to this particular location. So I had updated the acquisition scorecard segmentation and with the new videos, all right? So all the SAS code descriptions did done till date are over here. The scorecard segmentation analysis framework is discussed here, and the data preparation, data dictionary steps are discussed here. So all the 3 steps are over here that we have discussed till now, and that will be gradually updated, right? So over here, what we are going to talk, what we have been talking about over here is we had discussed about central tendency, dispersion, and probability theory and distribution. So in this particular drive, we have this section of readings and references, right? So I have uploaded the text, this portion with all the documents on the entire content on probability theory, distribution, and central tendency dispersion, and all these sections on readings and references will be gradually updated, right? And over here we are listing out the interview question list on statistics. Clear? So please, so we would be reading it up from here. The videos on statistics and predictive modeling is saved here. So I have introduction to predictive modeling techniques, all the videos being saved here on central tendency and probability theory and distribution. I will be uploading them as well as we go ahead, right? So yeah, so we will be, so you need to use the videos from there. You need to use the Word document from readings and references, and you need to visit these questions, which these are the tricky questions which come around. But apart from that, any portion of these concepts like these size quartiles, percentiles will come into play. right? So all the key concepts that you need to study are also has been listed over here, right? So when I talk about please practice, so for example in the section for probability distribution, we had mentioned that please practice some applications of classical probability theory. Now the question is, from where do I practice those sums or those applications? So if I come to this particular portion, introduction to the theory of probability, so you have some basic applications described here. Now you would see that there are, some mathematical proofs which are done, proofs which appear to you as very complicated proofs. Please do not go for them. They are done for the purpose of understanding. You can skip them, right? But the basic proofs, some basic proofs that are there, try to go through them, right? So for example, you don't need to understand the Bonferroni's proof, but it's good if you know what the Bonferroni's inequality is. So for example, when you are starting conditional probability, you don't need to know the proof, but the structure of conditional probability is something is good if we get to know them, right? Right. So all the detailings are done over here, right? So you can download them and you can go through them. You, if you are not comfortable reading the proofs, you need not do the proofs, right? Okay. So do practice them. So these kind of the basic applications of probability theory is available on Google, and also you can look up any of these class 10, 12 applications which are there. But please do study the concept of conditional probability and Bayes theorem. They are really very important. Right? So we'll start off our discussion for today from the concept of from sampling theory distribution. So this is going to be the topic on statistical inference. Statistical inference, which will comprise of sampling, estimation, and testing of hypothesis. Right. So these are the key list of questions that would come from here would include the following. Okay. So the first question that comes here is, okay. mm, Okay, so first let me start off with the concept, with some basic concepts, right? So one of the questions that they say is, they often ask is, explain the concept of random sampling. right? The next, a follow-up question to this is explain a step-by-step analysis, a step-by-step description of performing the random sampling. Now, this is a very tricky question. Now, we all know, like when I talk about random sampling, what I'm talking about is simple random sampling, right? And there can be two possible, so there are two possibilities of simple random sampling. So, one set of simple random sampling is when we are with simple random sampling with replacement, and the other is simple random sampling without replacement, right? Now, the first thing that comes over here is that there are so when you are doing random sampling, what you are essentially doing is you are randomly choosing the data points from the population and you are creating a sample from there, right? So when you are choosing the data points randomly, so there are two ways we generally use. One is when we are kind of doing it in SAS, especially, what we do is we use a so we have the proc survey select function, which helps us do the simple random sampling with replacement. And the second one that we use over here is we use a we use the uniform distribution to generate random numbers and then split the data into development and validation, right? So if you are asked on question like so if you're asked a question that how would you be kind of doing this or how would you be doing the sampling exercise, right? So there are, and when you are asked to explain the step by step function, right? So there are, so I would ideally go about answering it this way. So first of all, I'll put down the assumptions of doing a simple random sampling. Right? I'm not talking about WR or WOR. Generally, when you have a sufficiently large sample size, I would ideally do a simple random sampling without replacement because uh, because there are multiple random points, and by doing a without replacement, my development sample and holdout validation sample will have mutually exclusive set of records. However, if my sample size is very small and restricted, or I want to do multiple random, I want to create so that I cannot create multiple random samples, I can use a simple random sampling with replacement, right? So for example, the kind of validation, this is the kind of validation that I would like to do when I'm trying to do kind of a bootstrap analysis, or I'm trying to assess the stability of the model estimates. I would like to do a simple random sampling with replacement. But when I am trying to do when I'm trying to divide the data into development and validation sample, I would want to use a simple random sampling with replacement, right? I mean without replacement, so that the so that the records in the development sample and in the holdout sample are mutually exclusive. So assumption of simple random sampling is that the population should be normally distributed. That is symmetric in nature, right? So I need to first of all test for symmetricity. So how do I implement this? Before I'm doing a sample, my tests will be tests of symmetricity, right? Guys, just give me a second. Someone is at the door. Just give me a second.
This conference will now be recorded.
Okay. So the tests of symmetricity. Now what are the tests of symmetricity? So the kind of tests of symmetricity are the one that we have studied, or the kind of question that we have discussed for for assessing, or for testing whether the population is normally distributed or not. So these are the kind of So where we are kind of trying to assess the, so we can use the key descriptive moments, the key elements of the distribution, central tendency and dispersion, or we can use some kind of statistical checks to assess whether the population is more or less symmetric or not, right? Once I'm sure that the population is symmetric and that there are no element of and that is not skewed, or there is no element of heterogeneity, then I move to do the uh, so I kind of move to do this particular test. The I kind of move to do the sampling, right? So what are the kind of tests of symmetricity? There can be central tendency tests for normality. There can be statistical tests of normality. So we'll discuss these tests when we are talking about testing and hypothesis, etc. So once we have done this, so one with this assumption testing, we move to the next part. So now is the choice of the random sampling method.
Uh, Tanmay, um,
Yeah.
Tanmay, I have a question here. So, there is one theorem which says, according to the simple random sampling, sampling distribution theorem says that uh, if we have enough samples to make a distribution and we divide the distribution, then the population will anyhow come out to be normal. So, do we still, if the population size is greater than 30, is it necessary that we do
No.
the
Yeah. So
symmetric
what you
test?
are saying is correct. So I think what you are talking about is kind of the central limit theorem, right? So
Yeah, correct.
basically, yeah, but there is slight difference in the central limit theorem and the sampling exercise. So what it says is, what the central limit theorem tells us is that as the sample size tends to infinity, or when the sample size becomes infinitely large, right, the distribution of the estimated, the parameter estimate tends to the parameter. Right. So basically, what it says is, let's say I have a sample of 1 lakh observations, and I keep on creating samples of 100. Right. I create 100 samples of 100, or let's say 1,000 samples of 100 observations. And on all those 1,000 samples, if I compute the sample mean and I take the distribution of that sample mean will be closer to the population mean than if I take like only 10 samples and compute that mean. Right. Now, the entire idea of central limit theorem is that any kind of asymmetricities in your population can be taken care of in terms of parameter estimates, right? If you are using large number of samples. Now, when we are building the sample, we build only two samples, right? So one is the development sample, the other is the validation sample, right? So when I'm dividing that data into, when I'm doing that 70-30 split for building my model, I need to ensure that, right, that the two samples are representative of each other. So there's a representative check as well. Now, if I'm doing a random sample, a simple random sample, that's what I'm saying. Now, if I'm doing a stratified random sampling, then it does not matter if there are heterogeneities in the data, because I am considering a representation of each of the categories that is creating the heterogeneity in my sample, and I'm creating a simple stratified random sampling. But if I'm using a simple random sampling to do it, then I need to be sure that there are no asymmetricities in the data, because what can happen is, if there is sufficient, if there is element of a heterogeneity in the samples, then let's say when you're doing a random sample, those a part of those asymmetricities get reflected more in the holdout than in the validate development sample. So what will happen is, or in the training sample, so what will happen is that your models will, so your model performances will fluctuate between the development and the holdout, right? So conceptually, so if you have to do a conceptually sound sampling framework, right, using simple random sampling, you need to ensure that your population is normally distributed. Clear?
Yes, Tanmay.
Okay. Now, this choice of the random sampling is, when I'm doing a random sampling, I do one way is to do is using the random numbers from uniform distribution. right? And divide it into a 70-30 split. So we have studied, so we have seen in the last question that, suppose X follows a uniform distribution. So this question number one can be a follow up question to question number six, or you can use this concept of question number six in answering question number one. So the choice of the random sampling method, or use random numbers from uniform distribution, or using the proc survey select, the SAS function for performing random sampling, right? Now the question that comes over here is that with random numbers from, like, using the uniform distribution, so there is a limitation with, so the limitation is limitation of using ran uni function in SAS, using the random number approach, is that there is a lack of replicability, right? So because when you are using the random numbers, right, your sample, it's difficult in SAS, it's a bit difficult to freeze the sample. Now, in Python, you use a random uniform distribution, you split it into 70-30. But there is this seed function which you use, you put a seed equals to 1, which freezes the sample, right? So that problem of replicability using ran uni function is not there in Python. But in SAS, if you're using a ran uni approach, there is a lack of replicability. So there can be a lack of replicability issue. So what we do is, so advantage of using proc survey select is the proc survey select approach. So advantage of using the proc survey select is that the sample can be frozen using the seed function. So if you specify the seed in a random frozen by specifying the seed, right? So it can be by using the seed, right? So once I specify the seed in a proc survey select function using the random, when I'm doing a simple random sampling, the sample size gets frozen. So every time, if I'm developing the model and it is going to the person, right? So if it is going to the validator, and the validator runs the code and he matches the sample will match exactly 1 to 1, right? So that is one of the challenges with the ran uni function, right? Using a random number approach. So both of the two approaches are there, but that's the reason why we choose the proc survey select approach in SAS. And finally, what we have over here is so once you have created the sample, the next step is the representativeness analysis. So what we do is we analyze whether the samples are representative in terms of, number one, the target variable, That is whether the bad rates are representative across the development and the holdout sample or not. Because if it is not, then you may develop a model, let's say, with a 10% bad rate, and then what you do is you validate the model. You're validating the model on a date on a holdout sample where the bad rate is 7%. So the model performances will dwindle, right? So if it is 10% on the development, you would expect either a 10.5, 11%, or a 9.9, 9.8% of a bad rate, or slightly more than 10%. So something like that. They should be very similar. So the fluctuation between the development data and the fluctuation between the bad rate in the validation and holdout and the development data should not be more than 1%. Ideally, max possible, depending on the lack of availability of data, it should not exceed 5%. And then, like, key profiling variables, right? So there's some key variables in terms of it, such as lending variables, like loan product variables. You would have uh, borrower characteristics, etc. Right? Now there is another thing of so creating a balanced or an unbalanced sample, or unbalanced sample, right? So basically what you can do is to in credit risk model, we know that the bad rate distribution is kind of skewed, right? Now there are two approaches. So one case, what we do is we use the distribution as is. In some cases, a balanced sample is created with equal proportion of good and bad in the model, because it is believed that the skewness of, if a variable is too skewed, right, then that can impact the robustness of the model, and hence the balanced or the unbalanced samples are used, right? Balanced on unbalanced samples. So in a balanced sample, you have uh, equal proportion of events and non-events. Now this is applicable only for cases where you have categorical target variables. Now if I have a continuous target variable, then you can use the data as is, right? So even like I develop most of my models on unbalanced samples. So unequal proportion of events and non-events is your unbalanced sample. Right. So these are two kind of samples that you can look at, right? So basically, the steps for would be to, first of all, if I'm doing a simple random sampling, to assess symmetricity, then look into the choice of the random sampling method, then assess whether I would like to do it using ran uni function, or I would want to use a proc service selector to a simple random sampling, then representativeness analysis, and assess whether the samples are represent the development and the holdout sample created are representative or not, right? And finally, to assess whether do I create a balanced or unbalanced sample. Now, ideally, if anyone asks you like which is giving you a better, so which is a better model, like which is the better kind of sampling. So basically, for a simple random sampling, you always have the answer that lack of like random number approach, if executed through SAS, can have a lack of replicability. Right, the sample size may not be exactly the same that on which the development validation has been performed by the developer. So to freeze the sample using proc service select and performing a simple random sampling with or without replacement is it's a more better approach from the replicability perspective, and the representativeness analysis obviously holds, right? So the one which gives the more representative sample, a more replicable sample with a better model estimate, would be the better approach for that respective data, right? So these are broadly the steps that you would perform while you are doing a random sampling. Now this is a very common question which often comes in these kind of interviews for credit risk, right? So this is something that we need to look at, right? Okay, the second question. Now another very common question which kind of comes up on sampling, right? So on sampling, so like in terms of sampling approaches, yeah. So is the difference between a simple random sampling and a stratified random sampling. Now, when I talk about the difference between a simple random sampling and a stratified random sampling, obviously the difference lies in the usages, right? So basically, let's say you have a data set uh, where you want the representations of specific categories to happen, right? So let's say you are building a regulatory model, right? Now, if you are building a regulatory model, then what you need to do is you may require the representation of specific categories in specific proportion. So basically, let's say the in a population distribution, uh, or let me put it this way. Let me frame this question in this manner. When would you prefer a simple random sampling, sorry, a stratified random sampling over a simple random sampling? So I would actually prefer a stratified random sampling over a simple random sampling when there are certain categorical variables in the data where there's a requirement that certain key categorical variables in the data which represent the portfolio, the customer behavior, must have the exact distribution in the development and the validation sample as it is in the population distribution. So, for example, consider the product type distribution, right? For credit cards, right? So let's say there are different credit card products like we had discussed last week, right? I think we spoke about some, the product level distribution for credit cards. Now, let's say the composition is as follows. So basic comprises 50%, advanced comprises of 18% or 28%. Gold comprises of 15%, 12%. So that's 90. Platinum comprises of 8%, and diamond comprises of 2% of the overall portfolio of the bank. Right? Now, if they are comprising of, you know, or if this is the distribution, right, the business requires this specific distribution to be represented in both development and validation, then a stratified random sampling is done or is preferred over a simple random sampling. Is preferred over a simple random sampling, because if you are doing a simple random sampling, this exact distribution may not be represented in the development and the validation. So maybe the development has 51% of basic and the other has 49%. But if you are seeing the shift, there, there is not a significant shift, but the exact representation is not there. If certain categorical variables need to be represented in specific proportions in both the development and validation data, then this then this is what is done, right? Otherwise, there is no. I mean, there is no. Uh, so otherwise, a simple random sampling can be performed, and these distribute and the shifts of the key distributions can be checked through the representative analysis. And if you see that there are no major shifts, there should not be problem with the simple random sampling approach. However, if this particular specification is involved, then what we need to do is we need to ensure that a stratified random sampling is performed. Right? Now, these two questions often come out as a part of the discussion. It often comes out as a part of these interview discussions, right? Okay. So Devojit has a question with for me. He says that in credit risk modeling, we generally have unbalanced data having around 3% bad rate. So do we generally try to balance the data or build a model on the unbalanced data itself? So Devojit, this is what I was saying, right? So we often in credit risk, we can often we build model on unbalanced data. However, it depends on the value or the observation count of that 3%. Let's say if that 3% is around like 3 lakhs or 1 lakhs, because in a retail portfolio for a bank you can have uh, the retail portfolios can be as large as 3 million, 4 million records. Or say for example, if I'm looking at a credit card portfolio for Citibank, so then it can be around 100 million records, right, in a overall portfolio. So 3% of the bad rate out of that 100 million is 3 million, right? So if you have 3 million bads across at a global level, so if you're looking at, even if you're doing a regional model, you have good, like, you can have 50, 60 lakh, like 3 to 4 lakhs of borrowers, right? So so then if your sample is like, let's say you have some 5 million or 6 million records, right? And in the 6 million, you have a 3% bad rate. and you are doing a development sample, right? So then you can actually select out a smaller sample out of it and then do a balance on a balanced classic, or you can just develop it on the unbalanced data as well. So it depends on the modeling approach that you are using. However, given that the business group requirements or for regulatory model regulators requirement is that the portfolio should be modeled as is and the loss behavior should be reflected as is. So therefore, most of the modeling approaches in credit risk models, at least for regulatory models or building uh, risk management models, generally use the unbalanced approach rather than using the balanced approach. Right? Okay. So these are the two more. So these are kind of questions which would come around sampling, right? So if I have to talk about the sampling concepts, the key concepts on sampling that we need to study, they include simple random sampling with replacement, which is SRSWR, simple random sampling without a replacement, which is SRSWOR, stratified random sampling, advantages and limitations of simple random sampling, advantages and limitation of simple random sampling, uh, representative analysis. Now, for this, you need to refer to the EBA GL 2016-17. This is the IRB repair approach. The reason I'm saying it is that when we are generally doing the representative analysis for for a what model do I say, for a simple scorecard, right? The representative analysis is only limited to the is mostly limited to the looking of the represented in the target or the target variables between the development and validation. But this guideline for the IRB repair approach from the PD section provides a more comprehensive framework for doing this, right? So for doing the representative analysis. So that is the reason why this EBAGL 2016-17 IRB repair approach is something I'm referring. So if you go to the representative analysis section in the document, it lays down different guidelines for doing the representativeness of PD models, LGD and EAD models separately. So you would know how it is done for each of those. For a scorecard, the representative analysis described for for the IRB repair approach would hold, right? For the IRB repair, PD model would be applicable for scorecards, right? But to refer to this document because it gives a very comprehensive analysis. So if you are answering the representative analysis based on the IRB repair EPAGL 2016-17, right? It would be the answer would be a 10 on 10 for for any PD model. Right? Clear?
Yes, Tanmay.
Okay. The IRP repair document can be easily obtained from the net, right? Okay. So now the next question that I'll kind of go into is to talk about. So the next set of questions that we'll discuss around is on estimation, right? So on estimation theory. Okay. Next question is, what do you understand with the concept of unbiasedness of an estimator? Concept of an unbiasedness of an estimator. Yes. Can any one of you tell me what is it meant by the concept of an unbiasedness of an estimator? What is meant by the unbiasedness of an estimator? Okay, so let us try to understand unbiasedness in this manner. Just let me start with this. Create a numbers file. Okay, let us consider that. So, interview questions on statistics. Questions. Basic statistics. This is concept 0. Unbiasedness of an estimator. right? Okay. Now let us say that I have a data variable x with me, right? And I'm generating numbers between say 100 and 200, right? And I'm just putting it across, right? This is variable, and I'm just taking, right? Now, what I'm doing is I'm just creating some samples from here. So, sample one. So, sample one. So, let me take this sample. So, let me, because this is a random number generated sample. So, just let me create uh, okay, so I'll create, let's say I'm just creating a sample as hold on. So let's say I'm just creating some numbers like 10, 101, I'm putting in 112, I'm putting in 143, I'm putting in 122, I'm putting in 135, I'm putting in 167, I'm putting in 133, I'm putting in 123, I'm putting in 134, 125, I'm putting in 166, I am putting in 141, and I'm putting in let's say 150, right? So the first sample that I am creating is 101, 143, 166, and 141, 133. So I have five, right? So I'm creating another sample. So let's say I'm creating 112, I'm creating 122, I'm creating 135, I'm creating 123, 166, like this. So I'm creating with replacement, with replacement, right? So the numbers can repeat over here. So I have 167, I have 167, 166, 150, 101, 133. Right? So what I've done is I have created three samples. Now this has an average over here, right? So this has an average. So the average is 134, right? Now what I have done is I don't know what this population average is. I don't know the population average, right? That's unknown. So over here, what I do is so what I do over here is right. So what I've done over here is I've taken three samples over here, right? Three samples of size 5 each. Now observe that I have a distribution of the averages, right? So if I take the average from sample 1, so this is the first sample mean 1, this is the sample mean 2, the sample mean 3. Now if I take the weighted averages of these sample means, what do I get? This plus this plus this. So the weighted average over here is the fact, because you know, so the average over here is, I'm just doing a simple addition because all of them have a unique frequency. Now if they had different frequency, it would have been a frequency weighted average. So observe that the weighted sample mean is 137.26. So it is coming closer to 134. So if I increase the number of samples more, I'll be able to come closer to this, right? So what is the difference between these two between the sample and the population mean over here? It is 137 minus this divided by this. The difference is 1.8%, 1.85%. So one thing you can see is that if I increase the number of samples more and more and I take more and more sample mean, this the average, the weighted average of the sample mean should tend to the population average, right? So the concept of unbiasedness itself states that if I have if I have a distribution of the averages, I will expect, so the estimator would be an unbiased estimator if the weighted average of the sample means is equal to the population mean, right? So mathematically what we say is that expected value of the sample statistic is equal to the population parameter, right? Expected beta hat or expected theta hat is equal to theta. So this is what the definition of the concept of unbiasedness is, and the interpretation is as we had discussed in the Excel sheet. Right? Any questions up to this point? Is this concept clear to us? The expected value of the sample statistic is equal to the population parameter.
Yes, Tanmay.
The next question that comes over here is that I have described the entire process of unbiasedness for you, right? Now, if I have define the entire process of unbiasedness for you. What is it? What do you think is the limitation of using unbiasedness as a property of a good estimator? So, what is the limitation of using unbiasedness as a property of a good estimator? Because when we do the linear regression model, we say it's a blue estimate, right? The best linear biased estimates. But we just do not look at it as the linear unbiased estimate. So why is it that unbiasedness, or what do you think is the limitation of unbiasedness as a property of a good estimator from the description of unbiasedness that we have just seen in this Excel sheet? So from here, what can you make out? So just have a look at this example. The limitation of unbiasedness is itself hidden in this example. Okay, so to explain this, let us relook into sample 1. So this is sample 2, this is sample 3, right? So I will take these records and I will put it here. Now what I'll do is I'll add a few more records. So you have 123, you have 123, you put in 1, 1, 2 over here, right? And you put in all, so I'm just putting in 134, right? So over here I'll put in 101, I'll put in 125, and I'll put in 141. Over here I'll put in 112, I'll put in 141, I'll put in 135, right? Now what I'll do is I'll again do the average. Right? Now if I compute the weighted sample mean, now check the fluctuation. I'll take the APS, the absolute value of this. So over here, you will see that the percentage has changed to a difference of 1.5 from 1.8 just by increasing a few records in the sample. So one of the important observations for unbiasedness is that unbiasedness of an estimator, right? The unbiasedness of an estimator as a property of a good estimator is based or is a function of the sample size or on the number of samples. So if you are not choosing a very optimal size, it is largely possible that you may get some differences from your uh, from your population estimator, right? So one limitation of uh, this particular method is of unbiasedness is that unbiasedness is a function of the sample size. Unbiasedness of an estimator is a function of the sample size. Hence, results can be unreliable on the distribution of the estimator for a given sample size. For a limited sample size. Hence, this particular estimation is looked into, or this particular or this particular measure is not looked in solidarity. It is looked in with another measure. So your unbiased estimator will be a better estimator if it is giving you the minimum variance in the estimation process. So that's the reason why you have the best linear unbiased estimator, not only the linear unbiased estimator, or you do not have only unbiased estimators. You look into linearity, you look into minimum variance along with unbiasedness of the estimator because of this reason, right? Hence, unbiasedness is not the most important property of an estimator, right? Does this make sense for us? Any questions up to this on this point? Okay. So what are the other important properties that we need to understand about an estimator? What is the most important properties of an estimator? The most important property of an estimator is the consistency of an estimator. That is whether the estimator has the ability to capture all the informations about the distribution of the population parameter, right? So whenever you are asked on this question, you start by listing the important properties. They are unbiasedness, consistency, efficiency, and fourth is consistency and sorry, sufficiency.
Sufficiency.
So,
Uh,
please tell.
Tanmay,
Yeah, tell me.
okay. So, Tanmay, but for an estimator to be a good estimator, the four properties should be satisfied, right?
Right. But if you know what it is, the idea is like this, that if you may have an estimator which is an unbiased estimator, okay, or which is a biased estimator. But if that estimator is a consistent estimator, that is as the sample size tends to infinity, the sample estimate tends to the parameter estimate. Then, despite the fact that this estimator is a biased estimator, you can use that estimator form, right? If consistency, efficiency, and sufficiency is satisfied. However, if an estimate is unbiased estimate, but the condition of efficiency is not satisfied, then you may not use that estimator. So while unbiasedness, consistency, efficiency, and sufficiency are the four important properties of an estimator, right? Sufficiency is considered to be the most important property because it has been seen that if sufficiency of an estimator is satisfied, the other three are satisfied by default. However, it is not true otherwise. So think about the best linear unbiased estimator for a linear regression model. For the population mean, it is a sample mean, x bar, right? Now, if you think about an x bar for a normal distribution, it captures all the information about the distribution. It has sample mean x bar, x, it has a sample observation, it has the population mean mu, it has the population distribution sigma, right? So if I am kind of, and x bar follows a normal distribution with mean mu and a variance sigma square by n. So the distribution of that sample mean x bar contains all the information of the population distribution, hence is sufficient. So if you test unbiasedness, X bar is unbiased. If you test consistency, X bar is consistent. If you test efficiency, X bar is efficient. That is, if you use any other functional form compared to X bar, the variance in the estimations will be much higher compared to that of X bar. So that's how this is formulated, right? So that is the reason why that when we have the most important properties of an estimator, right? So listing the important properties, unbiased, consistency, efficiency, sufficiency. So that is what the difference is. So if someone wants to test your understanding of the uh, parameters, like if they want to test your understanding of uh, the fundamentals, right? So this is a point where they can come and kind of try to hit you down, right? So they may come they may try to hit you on this part. So over here, unbiasedness so that's why these four concepts are important. So I will, like I had given you for distribution and central tendency, I will also share the document with you for sampling distribution, sampling estimation, and testing hypothesis, right? So this is an important point, right? So in terms of concepts over here, there will be four concepts which you would need to study over here. So obviously the concept of unbiasedness of an estimator, sorry, the concept of an estimator versus parameter, of a statistic versus an estimator. Now this is a very tricky question. What is the difference between a statistic versus an estimator? Can anyone tell me what is the difference between a sampling statistic versus an estimator? Consistency, evidence, sufficiency, mathematical formulations. Mathematical formulations. And for sampling distribution. Yes, what is the difference between a statistic and an estimator? I just need to put this question down. The difference between a statistic and an estimator. Yes. What is the difference between a statistic and an estimator? Anyone? Just say. I mean, it can be right, it can be wrong, nothing matters. Just say.
Mm, then I don't know the definition per se, but
Just the concept. I need the concept. I don't need the exact definition.
okay, so I think so. This the mean of a population or a mean of a data is a statistic, uh, but the uh, estimator
You
is
are close,
used to.
but yeah, but it's slightly different. You are close, but slightly misplaced. So basically,
Okay,
think about this example, right? So think about this simple example. Now, over here, you have sampled me. So what have you done? You have computed three sample means, right? Sample mean one, sample mean two, and sample mean three. And for those sample means, you are computing a weighted average. So this weighted average is nothing but the mean of the distributions of the sample mean.
yes,
So if you are computing a weighted average, you can also compute a standard deviation for them. So what is the standard deviation? I'll put a stddev, a standard deviation of these three values.
so this will be standard deviation of the distribution.
Standard deviation of the sample means,
Sorry,
correct?
so, the formula, Tanmay.
The standard deviation, the simple standard deviation formula.
The variation from the mean. How much variation is there from the mean?
So this mean the weighted average is 137. Now
Yeah,
the mean of sample 1 has a deviation from 137. The mean of sample 2 has a deviation from 137. The mean of sample 3 has a deviation from 137. So the standard deviation shows the average fluctuation in the sample means.
yeah.
So if you think about it, so the sample mean means has a distribution which has a mean of 137.26 and a standard deviation of 5.91. So it means if you see this distribution, what it means is so there is a mean and a distribution to this sample mean series, right? So if I write it something like this, sample mean 1 is 136.8, sample mean 2 has 131.6, sample mean 3 143.4. So you can see that this is a distribution of the means, right? So the sample mean is having a distribution. So each of these sample means are an estimator. And when you are looking into this distribution of the estimator, that is a statistic. So very simply, if I have to define this, a statistic is an estimator with a sampling distribution. So this each of the sample means are an estimator of the population mean. But when you are creating multiple random samples, and for each of those samples you are trying to find out the mean, right? You are getting a distribution of the sample means. So that distribution of the sample mean is the statistic. So that is the reason why we write. So when you are doing a multiple random sampling and you're creating an estimator, that's the reason why you will see that X bar has a distribution in a linear regression model. So it says that X bar follows normal distribution with mean, mu, and sigma square n. So there's a standard, that's the standard error. So statistic is an estimator with a sampling distribution. Clear?
Tanmay,
Is
can
this
you please
example clear to us? Sorry?
repeat? I mean, it's kind of the
Okay.
last. Can you repeat?
See, so this is my population, right? Correct? So this is the population of the data that I have.
Yeah.
Now, I want to predict the population mean. I want to frame an idea of the population mean, right? Because the population mean is generally unknown to me. So what am I doing? I need to use the sample and I need to find out that. So I want to predict the idea about the population mean. So what I do is I create a random sample over here, right? Now when I'm creating a random sample over here, I know that it is random, right? So just by creating one sample and forming a mean and just calculating the sample mean, I cannot rely myself with the fact that the mean is calculated correctly, right? So over here, what I'm doing is I'm creating the first sample. With the first sample, I get a sample mean. Now, given that I have the sample mean with me over here and 136, I just cannot say that because my sample mean is 136, I say the population mean is 136 or somewhere close to it. It might be that the random sampling has not been done correctly for a given sample. So, what I do is I do multiple random samples. Correct? Now, when I'm doing the first random sample, I'm computing the sample mean. Now I'm trying to estimate the population mean with the sample mean, right? So therefore, the sample mean is a estimator over here, right? Now I'm creating multiple random samples, and for each of them, I'm computing the estimator sample mean, right? Now, if
Yeah.
I'm doing so, I am now having a distribution of the sample means. Because for sample 1 I have a mean, for sample 2 I have a sample mean, for 3 I have a sample mean. So I have 3 samples and 3 means. So there is a sampling distribution of the means. Correct?
Yes,
So there is a
correct.
distribution, right?
Yeah.
Now, why there is a distribution? Because I'm getting multiple random samples. I'm creating multiple random samples and computing the sample mean for each of them. If I'm computing the sample mean for each of them, then I'm getting a value. So basically, I have a frequency distribution associated with it. 136.8 has occurred one time, 131 has occurred once, 143 had occurred once. So I have a sampling distribution associated with them, right? A frequency distribution. So therefore, now I have a distribution of the sample means. When I'm having a distribution of the sample means, I can define the distribution with a mean and a standard deviation, right? So when I can do that, so when this sample mean has a distribution associated with it, so when this estimator has a distribution associated with it, when there is a distribution of the estimators, that distribution is known as a sampling statistic. And that statistic has a sampling distribution.
Okay.
Yeah.
Yeah. Thank you, Tanmay.
So this is a very tricky question which often comes in that we say that okay, the sample mean is an estimator for the population mean. So suddenly the interviewer crosses you and says, "Are you sure it's an estimator?" So technically, what the interviewer wants to know is whether it is an estimator or whether it is a statistic, because these conceptual questions or these concepts, these conceptual points become very important when you are trying to discuss, or when you are trying to hire someone new into the modeling professions, right? So basically, when I am conducting interviews, there are generally three rounds of interviews that are conducted. The first round of interview is where I'm asked to interview the candidate on his understanding of model development, right? If he has worked on, and if he's not worked on it, if he's coming in from a monitoring team, or let's say from some other teams into a development profession. So then the first round, while we ask them things around their CVs, a certain time is dedicated. Let's see if it's 30-minute discussion, at least 7 to 8 minutes or 10 minutes is dedicated to asking questions on basic statistics to understand whether the person can read basic statistics or not, right? So once I'm sure that he has a sound understanding, then in the next round he's promoted to the next round where he's grilled more on the validation, development, and technicalities of development, right? So that's where the concept of variables are, what kind of variables, and so on, these kind of questions come in, right? But in the first round, right, in the last 10 minutes of the first round, we are asked to grill them on it, right? When this person moves to the second round, the first 5 minutes is spent on understanding his CV and his mindset, and the second half, or the remaining 20 minutes, 25 minutes, is spent in grilling him on his understanding of model methods and regulations. So over there, it is divided between regulations and modeling methods, right? So in the first round of any interview, you would see the first, if it's a 30-minute interview, the first 5 to 6 minutes are there, or 10 minutes are there, understanding your CV. Next 10 minutes to 15 minutes will be on understanding your understanding of statistics and methodologies. And the last 8 to 9 minutes would be spent on understanding your software, understanding if you've worked on a software. So, so that is the way the first round will be structured. Right now, it may differ from organization to organization. Some now, if you are someone who has already worked on development, you're automatically expected to have an understanding of these methods. So from there, moving on to the next round. In the first round, you would be mostly questioned on development and validation questions. Your understanding of statistical methods will take a backseat. It would go to the last 6 7 minutes, and in the next round, you would be questioned more on guidelines, regulations, and your understanding of software. The third round is mostly soft skills and understanding the stakeholder management and all these things. So the way you have to prepare for your interviews, so depending on the profile that you are selecting, so this preparation would differ, but the components would remain the same, right? So, so that's the way we are going to prepare. And this, so these are a set of few questions which are most oftenly asked, right? Which are most often asked. So what we need to do is we need to gather an understanding on this, right? So we have, so let's take a pause here for the day. We have gone till estimation. Now the next part is testing hypothesis. So in tomorrow's discussion, we'll take up linear and logistic, and along that, I'll be talking about testing hypothesis, because without those modeling algorithms, classification algorithms, it is not really possible for us to us understand this concept of testing hypothesis. Right? So we will be discussing linear and logistic and testing hypothesis in tomorrow's session. So these three classes will complete the interview question list on statistics and modeling. And from there, what we are going to do is we are going to move into the next concept, which is the next component, which is model development and validation skills, along with the regulatory frameworks. Right. So we will discuss them separately. Right. So thank you for your time. Uh, please refer to the updated list of these questions, and we'll meet tomorrow same time, and we'll take it up from there. Thank you.
Tanmay,
Yeah.
Tanmay, can you also share the documents for this and like the reading material that you have shared
Yeah,
for
I
the
will put the
other?
reading material on the same drive location where you have your reading documents for central tendency and probability theory. I'll put sampling over there.
Okay, thank you, Tanmay. And also
And
for
yeah,
this
for people who are
hypothetical.
joining the IFRS 9 classes, I'll just reopen the link in 2 minutes' time. Please rejoin back. Thank you.